Hello and welcome back to CS492A, Unconventional Computing at KAIST in fall 2024. Last time we discussed about conventional computing, and today we're going to continue with this chapter 1, conventional computing, meaning various ways of realizing Boolean gates and other forms of digital computing. That means processing discrete data using finitary means. Everything is finite. Like we have finite amount of memory, we have finitely many operations per second, and every computation must eventually terminate. That's conventional computing. And today we're going to finish with this chapter 1, and then we're going to start talking about chapter 2. Chapter 2 is about asymptotic computing. Some people may call it infinitary computing, but I'll explain why the term asymptotic computing is more appropriate. And you see how we gradually move from traditional to unconventional forms of computing. So with that said, let me start by sharing the slides of still in chapter 1 about conventional computing. Conventional computing means digital computing, means Boolean gates and combining Boolean gates to form Boolean circuits. And we discussed several unconventional ways of realizing Boolean gates. Traditionally, this is considered to be electronic computing, but historically it started with mechanical computing and then moved to electromechanical computing and to electric computing. And one nice way of recalling mechanical computing, we saw this kind of reproduction of Konrad Zuse's, the gates that Konrad Zuse used in his Z1 computer. And I gave you kind of this homework assignment to figure out what is the third of these gates that we considered. So this is an AND gate, right? Logical AND. The blue, yellow, and the two yellow bars indicate the two input signals. When a yellow bar is pushed down, it means 1, it means a signal is present. And the blue bar indicates the clock on the right, and on the left, it indicates the output. And you see, only if both yellow bars are pushed down, if both input signals are 1, then the blue bar moves out on the left. So no, it doesn't move out on the left. Now it doesn't move out to the left. And now it moves out to the left because that's an AND gate, right? And the second gate we considered was an OR gate. Now the blue bar moves out to the left. Also now the blue bar moves out to the left. And now it moves out to the left. But now it does not move out to the left because both input gates are 0. And this was the third gate. And I ask you to try to figure out what kind of Boolean gate is that. So let's see, when both input signals are 0, then the blue bar moves out, output is 1. If one input gate is 1 and the other 0, no output. Same here. And if both input gates signals are present, then also the output. So when both our inputs are 0, then we have an output. If both input gate signals are 1, then we also have an output signal. But if only or precisely one input signal is present, then there's no output. This is any answers? Can you write in the chat? What is your guess? What kind of Boolean gate is that? Oh, here's a correct answer. So you wrote the correct answer in the chat. Can you repeat the correct answer?
Yeah. Exclusive NOR.
Exactly, very good. Yes, thank you. So an exclusive NOR gate, which is the same as an equality test, right? So an exclusive OR is outputs 1 if the two input signals differ. If one is 0 and the other is 1. And this is the negation of that. That's a negated exclusive OR, which is also known as equality test. If both input signals are equal, if both input signals are 0, or if both input signals are 1, then there's an output signal. Whereas if both input signals differ, then there's no output signal. Very good. Thank you for participating in this spontaneous online quiz. Okay, so that being said, let's now move on with a recap. Yeah, mechanical SUSE Z1 computer had many faults, didn't run for a long time. That's why SUSE replaced it with an electromechanical computer using these relays. But these still often had some errors, some faulty operation, which led that to proceed to electric computing. And the essence of electric computing is based on these tubes, triodes. And this is different from electronic computing because of the high voltage it uses. And then we started moving from historical to more contemporary, unconventional computers based on fluidics. Fluidics means computing based on liquids and or gases, but without mechanical moving parts. Only liquids and gases are allowed to move, but no mechanical. So this kind of a solenoidal valve is not considered liquid computing. And essentially, liquid computing started maybe with Tesla, who invented this Tesla valve, which is kind of the liquid counterpart to a diode. Of course, here in a diode, electric current can only proceed in one direction, not in the other direction, which is unlike a classical resistor, which allows electric to move in both directions. And this is the fluidic counterpart. Liquid or gas can move freely from right to left, but not really from left to right because it creates a lot of turbulence with itself. And here we considered another Boolean gate in fluidics, a combination of an AND gate and an OR gate, where we have two input streams, A and B. And if they're both present, then they kind of cancel out and drop into this cup, which corresponds to the AND output. And if precisely one of them is present, then it leaves through the bottom exit, and that's exactly our exclusive OR. The negated one that we saw mechanically, but the original exclusive OR. And here we considered another gate, a combination of two gates. You see here the right exit, A plus B, and here you see the middle exit, which is A negated and B negated. And what you is not maybe explicitly clear, so let me emphasize from the bottom comes a powerful input stream. This is kind of like the power supply. You know, our digital circuits, logical electronic circuits need a power supply, right? And in fluidics, the power supply is with a high pressure stream that is always powered. And these A and B are the control streams. So imagine here's a high pressure input stream. And if there's no signal on A and B, then this high pressure input stream just passes through and leaves here. And no input signals on A and B. That means negated A is true and negated B is true. And therefore also the conjunction, the product means conjunction. So then there's an output stream here. Whereas if there's an input signal from A, then this input stream diverts the powerful input stream to leave here. Same if there's an input signal B here. And if they're both input signals, then even more so, the input stream gets deflected. Powerful input stream gets deflected by non-powerful control streams A and B. And this here is similarly kind of a amplifier. Here's a power input stream, and here's the low power control jet from top or from bottom, deflecting it, the powerful input stream, either in this way or in this way. And this is a way of amplifying the control jet, right? So the control jet has low power, but it controls and produces a high power output jet either here or here. So the input signal is amplified. Important part of fluidics, amplifying the input signal. Okay. And this was the basic ideas of the so-called flow deck computer, which was presented by Glaskin, Jacobi, and Reeder in 1964 as a way of fluid-based entire computer system. So this is fluidics. And in the last part, the next part of chapter 1, I want to talk about soliton computing. So let's talk a little bit about solitons, but before that, let's talk about classical waves. Solitons are kind of nonlinear waves. So for those of you who have already taken courses in physics, this may be a simple recap. For others, this is good to know about wave physics. So let's first talk about waves physics. Wave physics appears everywhere in physics, right? So, for example, light is commonly considered as a wave. Sound is commonly considered as a wave. And there are water waves, right? The ripples in the water. If you throw a stone into a pond, it throws great ripples that move, and that's all waves. And all these different kind of waves are governed by the same mathematical equation, the so-called wave equation, which is a second-order partial differential equation. U indicates the amplitude of the wave. This is the sum of second-order spatial derivatives, and U double point means the second-order temporal derivative, and C is the velocity, which is the velocity of light. If we're talking about what light waves, it's the velocity of sound. If we talk about sound equations, it's the velocity of water waves. If we're talking about water waves. And the essential property of this wave equation is that it is linear. So if we have one wave, here you see a wave created by an array of of springs, mechanical springs, right? And you see that this wave at every spring moves up and down, and this moves up and down, but with a different phase, and this creates the appearance that the wave is moving, although the springs are fixed. So, like with the waves on a pond, the water is not really moving sideways, it's just moving up and down, but it creates the appearance of the waves moving away from where you threw um, the stone. Okay, so waves move, but the actual medium does not move. Same for sound. If you speak, then the air moves only a little bit, but your sound moves from your speaker to somebody who is listening. So that's the essence of waves, and it has been long a question of what is the medium that moves when light waves move, and but that's advanced physics. Anyway, it's linear, which means if you have a wave with half the amplitude, like this, right, then it still moves with the same velocity, c. Velocity is independent of the amplitude. And if you have two waves, then they just superposition, they just add up to each other, okay? They move through each other without affecting each other. And that applies to sound waves, right? So if two people talk simultaneously, then still it's just the superposition, the addition of the two speakers. Electromagnetic waves, which are radio waves or light. Also, you can have two lights turn on simultaneously, and it will just be the two lights, yeah, moving in different directions. And this is true as long as the sound is not too loud, or as long as the electromagnetic waves are not too strong, or as long as the amplitude of the springs is not too large. If the amplitude becomes too large, then the effect becomes nonlinear. So let's talk a little bit about nonlinear waves. What is nonlinear wave? It's if we increase the amplitude beyond the linearity of the springs. So usually a spring, if you pull it twice as hard, it pulls back twice as hard. If you pull it half as hard, it pulls back half as hard. So this is known as Hooke's law, but there's a limit to it. If you pull too strongly, then the spring starts changing its shape and doesn't return to the original position. This is called the elastic limit of the spring. And if you, similarly, if you create a wave with too large an amplitude, then the movement is not described by a circular motion or a complex circular motion, but it starts to differ. That's a too large amplitude. That's where it becomes nonlinear here in these corners. And there are different mathematical ways of describing these nonlinearities. One famous that you may have heard of is the Navier-Stokes equation. The Navier-Stokes equation is used to describe waves or other motions of a liquid, such as water, if the liquid is viscous, so like honey, for example. Okay? Viscous fluids are described by Navier-Stokes equation, and this is a nonlinear equation. You may see the nonlinearity here, nonlinearity here, because there's u times the gradient of u. So this is basically u squared. U squared is nonlinear. Famous equation, one of the Millennium Prize problems about Navier-Stokes equation. So this is the Navier-Stokes equation without external driving force. And this is the Navier-Stokes equation with external driving force here. So 0 means no external force. F means there's an external force and maybe pushing the liquid in some direction. Navier-Stokes, one famous nonlinear wave equation. But here we want to talk about a different kind of nonlinear wave equation, namely those which admit so-called solitons. Solitons occur in many areas, actually, of physics, nonlinear waves, and but historically they originated from the so-called Korteweg-de Vries equation, which was named after two Dutch scientists, Korteweg and de Vries, and they tried to describe the behavior of water in the channels in the Netherlands. And they observed that the behavior of waves there does not follow the linear wave equation. So they came up with their own equation, so-called shallow water wave equation, Korteweg-de Vries equation. So here you see, actually people like to surf nowadays in these canals in the Netherlands. And here you see the Korteweg-de Vries equation, which is again an example, a different example of a nonlinear equation. Here you see one nonlinearity, u times u prime. U prime denotes the derivative. And there's another nonlinear term, u prime to the third. And here you see it's equal 0, which means there's no outside driving force. And if it is something like F, then it means there's an outside driving force. Now let's look at the mathematical simulation of such waves according to the nonlinear Korteweg-de Vries equation. Here you see two waves. And the first thing you notice is that they're traveling at different velocities. This cannot happen for the linear wave equation. In the linear wave equation, two waves always travel at the same speed, at the same velocity, regardless of the amplitude. But here it's so that the larger wave with the larger amplitude travels faster and eventually surpasses the wave with the lower amplitude, right? But the surprising thing is that they're still stable waves. They don't dissipate, they don't dissolve like a Gaussian wave, and they can even merge and re-emerge from each other unperturbed. However, note that the larger amplitude wave makes a kind of jump ahead of the other. So yeah, we see that if we plot the linear waves, and they would move, here you see the red wave would be, first they move at their usual velocity, and then a jump happens, and now the large blue wave is ahead of the red one, and the slow blue wave is behind the red one. So there happens a jump in so-called the phase jump during the interaction. And this is something that will be used later when we talk about soliton computing. Here's another example, two waves, right? And they meet, and then they re-emerge, and the one has made a jump ahead, and the other has made a jump behind. And here you see this, so this is the soliton equation, one example of a soliton equation, Korteweg-de Vries equation here. F has been added for the case of an external driving force. And this applies not only to shallow waters in a canal, but also it applies, interestingly, to optical fibers driven with lasers. And this is a common application, current application that people don't seem to really be aware of and appreciate. So because, optical fibers are used a lot for transmitting data, like across continents, for example, optical fiber, because they can transmit such huge amounts of data, and they use lasers because the laser provides so much power. But it turns out that the power provided by a laser is too strong for the linear wave equation, and therefore the light transmission in these optical fibers is described by the Korteweg de Vries equation, not by a classical wave equation. Put differently, light of higher frequency towards the blue or ultraviolet travels faster in these optic fibers than light of lower energy towards the red or infrared. So here you see moving us towards optical soliton computing, and here you see that contemporary laser favors and laser input deliberately use this nonlinearity to transmit more data in different frequencies, in different colors. And this was about scalar solitons, where there's only one dimensional data, like the amplitude, but light has a polarity, right? Polarized light. And this results in discussing about vector solitons, and this is how soliton computing works. Here you see an example of two input rays. They're depicted here as having different colors, but this is only for us to be able to distinguish them. In fact, they use the same color and only different orientation of the polarization. And here the two light rays do not meet inside the, this is going to be a Boolean gate. So they don't exit at the output location. But if we change the polarization, then actually they meet here. And this is a depiction of an AND gate, right? So, no, it's an OR gate. So if one of the light rays is present, then it will leave here at this designated location. And if two of them are present, then also they leave at this location because they they affect each other based on the soliton wave interacting with each other, one making it jump ahead of each other. So here you see what kind of gate is that? So this is this is supposed to be an OR gate, I think. And this is another gate. And this is the essence. This is how people realize, it's still digital computing, still based on Booleans, still based on bits, zeros and ones, but now with lasers in some nonlinear medium using solitons. So this is the end of our discussion of various ways of realizing Boolean computers. And I want to close with a discussion of the so-called Church-Turing hypothesis. So there's a so-called Church-Turing thesis. This is not what I mean here. What is the Church-Turing thesis? Church-Turing thesis is a theorem. It says that for a function from natural numbers to natural numbers, the following are equivalent. So this is the abbreviation for the following are equivalent. A function of natural numbers can be computed by a Turing machine if and only if it can be computed by a while program or fluke program if and only if it is mu recursive, if and only it is definable in lambda calculus. So remember, we talked about different models of computation, and I mentioned that Turing machines are equivalent to while programs, are equivalent to fluke programs. And in my course CS422 Theory of Computation, we also discuss mu recursive functions. We discuss functions definable in lambda calculus. Lambda calculus is something you might have heard of as the foundation of functional programming. And it has been proven that all these are equivalent. And this is called Church-Turing thesis. And this explains why the theory of computation is so successful, because 4 different ways of defining and investigating computability for functions on natural numbers are all equivalent. It started off as 4 different topics, 4 different investigations, which involved a lot of redundancy. But when it was proven that all 4 of them are equivalent, then one could easily transfer results from one setting to another one, such as, for example, quines, programs that produce their own source as output, can now be translated from one setting to another. And this is a shameless cross promotion to my course CS422 Theory of Computation. This applies to the qualitative setting, only being computable or being uncomputable, right? There are functions that are not computable. This is not with respect to efficiency, like P versus NP does not translate. And it's called Church-Turing thesis, not a hypothesis, because it was proven in the late 1930s, early 1940s, by a succession of papers from Stephen Colcleany, from Alonzo Church, and from Rosser, who finally put the nail to this. But this is not what I want to talk about today. Today I want to talk about the physical Church-Turing hypothesis and its variant, the strong physical Church-Turing hypothesis, which is a hypothesis, not a theory. It has not been proven, and it cannot be proven, because it connects between mathematics and physics, right? So this Church-Turing thesis is basically only about mathematics and theoretical computer science, but the Church-Turing hypothesis talks about physics. Namely, it talks about function being computable by a physical device. Remember, we've talked about many physical devices that realize computers, mechanical devices, electronic devices, electromechanic devices, and even fluidic devices and soliton devices. These are all different physical devices. And the statement says such a function on natural numbers can be realized by one of these devices or any other future such device. Then it can also be realized by a Turing machine. So that means all these devices are no more powerful than a Turing machine. And the strong version of this, you see why it's called physical Turing hypothesis, because it refers to physical devices, and that's why it cannot be proven, because there's no axiomatization of what is a physical device. You recognize one when you see one, right? But there are many open questions about physical devices. For example, does there exist a perpetuum mobile? Right? There's a laws of thermodynamics which says there exists no perpetuum mobile, right? But there's no proof of that, right? Or about magnetic monopoles. The Maxwell equations say that there exist no magnetic monopoles, but there's no proof of the Maxwell equations. So that's why this is a hypothesis, not a thesis, because it connects between mathematics via theoretical computer science. Turing machine is a mathematical device to physical devices. And there we cannot prove things. And the strong version of this theory's hypothesis says the same applies not only qualitatively, like in the Church-Turing thesis, but also quantitatively, taking into account efficiency, namely taking into account polynomial time computation. Something that can be computed in polynomial time on a physical device can also be computed in polynomial time on the Turing machine. But it turns out this is only one of the two sides of the coin of the physical Church-Turing hypothesis. The other side of the coin says the opposite. Anything that can be computed by a Turing machine qualitatively or in polynomial time efficiently can also be computed by a physical device. And this is often the the second part of the physical Church-Turing hypothesis that people tend to ignore or neglect because it seems so obvious, right? Right? Something that can be computed on a Turing machine can be computed by a physical device. That's what we've been discussing all the time, right? We've been discussing how to realize Boolean gates in a mechanical way, in an electronic way, in an electromechanical way using fluidics. So all these are ways of realizing a Turing machine, and your computer, your PC is also realizing a Turing machine using electronics, right? So what's the point about this item B? The point about item B is that recall our discussion about modes of computation, recall our discussion about whether your PC is a Turing machine or not, and we realize that maybe it is only an approximation of a Turing machine, but not actually a Turing machine, because a Turing machine is supposed to have unbounded memory, unbounded storage tape. Your computer has a lot of memory, but it is, after all, bounded. And if you use virtualization, then its memory is going to be huge, but it's still going to be bounded. So item B of the physical Church-Turing hypothesis is still something to discuss, something to keep in mind. And our focus here is on item A. Is it possible to compute more than a Turing machine can do on some sophisticated physical device? And in chapter 2, asymptotic computing, we're going to explore such possible ways of realizing computation using physical means that cannot be done on a Turing machine. But to be fair, it's going to be unconventional. That's the title, that's the topic, that's the subject of this course after all, okay? So this is the physical Church-Turing hypothesis connecting between what a Turing machine or while loop program or mu recursion in lambda calculus provably can do on the one hand, and on the other hand, which is up to debate, what a physical device can do. Can a physical device keep up and do everything that a Turing machine can or not? Can it only approximate a Turing machine on the one hand? And on the other hand, maybe some sophisticated physical device, such as a quantum computer, some people think that a quantum computer can do more, or at least can do more efficiently than a Turing machine. So that's the question A, right? Can a famous open question, so-called quantum supremacy, quantum computer can do qualitatively maybe the same as a Turing machine can do, but maybe more efficiently, maybe quantum computer can do something in polynomial time that a Turing machine cannot do in polynomial time. So that's a challenge to item A of the Church-Turing hypothesis. And your PC is a challenge to item B of the Church-Turing hypothesis. So this is a very important open question, because it's one reason it's open, because it cannot be proven or disproven, because it's not a mathematical claim, whereas the Church-Turing thesis are mathematical claims, and therefore they can be proven or disproven, and actually they were proven. So this is the end of chapter 1 on conventional computing, and also already the cliffhanger to the upcoming chapter 2 on infinital, or maybe better called asymptotic computing. To wrap things up, we talked about digital versus analog signals. We talked about digital models of computing. We talked about examples, and we discussed these examples, including your PC. Is it a Turing machine or is it a finite state machine? We talked about realizing Boolean gates using mechanical devices, using electronic devices, using electrical devices, using electromechanical devices, and using fluidics and using solitons. And we've ended this chapter with the discussion about the important Church-Turing hypothesis as opposed to the Church-Turing thesis, which challenges whether things that can and cannot be done on a Turing machine agrees or disagrees with the things that can be realized computation using physical device. Can a physical device do more or maybe less than a Turing machine? That's something we want to discuss in the next chapter. So that's all for now on chapter 1. And I'm going to take a short break now and pause the recording